Hello, and welcome back to AP Physics. So what would it look like if we took a simple harmonic oscillator, like a mass on a spring, that was oscillating back and forth, up and down. We put a pen on it, and then we pulled the paper along sideways. What kind of image would this thing trace out? It would trace out a sine wave. If you've done the lab or seen my demonstration of the lab on this, you saw that your car oscillating back and forth on the track did create a position versus time graph, which is pretty much what this is creating, of that was a sine or a cosine depending on where you started your car. Probably started out as a probably started out as a cosine. And what you would have seen is that we switched from here we're starting out with a cosine, I believe, function. The velocity was shifted by pi over 4, which gave us a sine. Okay, and then over here we had a phase shifted again, or we think of it as we were flipped and flipped from our displacement versus time graph, our cosine graph. So, and I was hoping that you would make some connections to calculus with these, and if you didn't make them, then I want to do those with you. So let's see. Here we have a sine graph, and the first derivative of that would yield a what? That would yield a cosine, and this is what we saw, and that's what we get when we take the derivative of x. We get velocity, and when we take the derivative of sine, we get cosine. And some interesting points. When x is 0, when our displacement is 0, notice our velocity is at its maximum. So that basically means that when the car was at its equilibrium position, or its displacement was 0, its kinetic energy, its velocity, was the highest, which is what we've seen from before. When x is at its maximum or minimum, so here we've got x at a maximum, our velocity was 0. And here we've got a minimum and it's 0. So, and that's to say that when the car reaches its outermost points, it comes to a stop briefly. Now, if we take our second derivative of sine, we get negative sine. And so the second derivative of displacement would be acceleration, and that's what your third graph should have looked like. And notice that when your x is 0, meaning you're at your equilibrium position, your acceleration is also 0. So because your net force is 0. When x is at a maximum, then your A is at a minimum. Okay, so basically, why is it negative? Why is it negative? Well, if this is acceleration, it's proportional to the force. And if we think of the force of a spring, remember the equation for force of a spring is F equals negative kx. Okay. Where basically that means is if your displacement of the spring is to the left, your acceleration is to the right. Your force is to the right. So, and that's why you're seeing that here. So dampened simple harmonic motion. Those were kind of the major things I wanted you to make connections with there. Just a couple other little things. So here we've got a dampened simple harmonic motion curve. This is what the shocks on your car, if you were to look at the displacement of the shocks of your car, they would look like this, or actually they'd be quite a bit more dampened. But we notice we're still seeing the same period. The last thing I wanted to cover was this. Okay. This you'll see on your AP Physics equation sheet. X equals A times the cosine of 2 pi ft. This is the displacement of a simple harmonic oscillator from the equilibrium position, which would be a line drawn down the middle here. And so the distance from the equilibrium position would be x as a function of time. Okay, so A is the amplitude, then you've got your cosine function times 2 pi times the frequency of and times time. So so again, this is on your equation sheet. I'm not going to make a big deal about this. You might see a problem in the on the homework on this, but you're probably not going to see one on the test along these lines. But you never know; it could be covered on the AP exam. Yeah. Okay, and that is all I wanted to go through today.